All right, guys, let's see what we're doing today. Actually, I know. So part of what you're going to do today is finish up that Half-Life lab, doing your post-lab questions. I'll be doing a Zoom to Wednesday, which is today, depending on when you're watching this video, at 8 a.m. to go over those questions with you. If not, if you missed it, there's a post-lab discussion video right here on your Canvas page. So that is due today. And this absolute dating notes as well is due today. That's what this video lecture is going to be all about. So if you were face-to-face with me Monday and Tuesday, you can do these notes by hand in your notebook, please, or you can type them. It doesn't really matter to me, although I'd prefer you write them in your notebook. If you are tuning in electronically or a Thursday, Friday student, here's your copy of the notes. Remember, you're going to need to make your own copy again, file, make a copy, make sure that you change the share settings to anybody with the link so that I can view the link when it's time to grade. All right, let's get started though, shall we? We did our lab using M&Ms to discover the half-life, but instead we're going to talk for a second about we did our lab to discover the half-life of elements, which helps us date rocks. We're a little bit off on our PowerPoint. Give me just a second. Quite a bit off. I hope that by doing the lab, you understood that as each time period or trial continues on, we're losing half of the amount of elements that we had in the beginning. So, for example, your last post-lab question asks, did the number of atoms you start with affect the outcome? Sort of, but not necessarily. It depends. So if you start with a lot of atoms, it's going to take you a long time to get through all of your stuff. But if you have just a few atoms, it's not going to take you very long before your half-life, your element breaks into something that is, or till your parent molecule will break down into your daughter molecule. So if I have 5 grams of carbon-12 and 5 grams of carbon-14, I can assume that one half-life has happened since the rock's formation, meaning that the rock is about 5,730 years old, because that's the half-life of carbon. So carbon-14 is my unstable isotope. It wants to get to carbon-12, which is stable. So it will break down. About half of it will break down in 5,700 years. So if I have a sample or rock with equal numbers of carbon-12 and carbon-14, it's likely that only one half-life has passed. In contrast, though, if I have a sample where I have a majority of carbon-12 and just a few carbon-14 molecules left, that means that many half-lives have passed. We'll look at a graph at the end of this, and we've watched it on the post-lab discussion, hopefully, as well, to help you better understand this. Actually, here is the graph. But we'll go into our introduction. We'll come back to the graph as well. So relative and absolute dating, there are two major ways that we date a rock, and this goes in the shaded section of your notes. We can relatively date them, so tell how old a rock is compared to surrounding rocks. We learned about that just a fuzz when we talked about fossils. We learned that the law of superposition tells us that the older rock layer in a sedimentary rock will be towards the bottom, and the younger rock layer will be towards the top. But we said, again, that's relative, so that's a ballpark range. To find our absolute age of a rock, though, in the late 1800s, we have discovered that we can track the half-lives of elements like carbon-14. We call this absolute dating. It's the actual number of years since the rock was formed. So while the relative was kind of a ballpark or a comparative, our absolute dating tells me exactly when that rock was formed. So that would be like if I were trying to tell you all your age, you would be exactly 13, 14, or 15 years old. But if I were to try and tell you your relative age, I would say that you're all about school-age students, right? So you all go to school, but a school-age student might be somebody who is 17 or 18 if we're in upper levels of high school, or it could be somebody who is in 4th grade, say, I have no idea how old 4th graders are, maybe 11. So that's a relative way to age you guys, just like relative dating gives us just a general idea of how old something is, while our absolute will tell us exactly how old something is. All right, we're discovering all about absolute dating today, though, in our lecture. Here's how it works. So absolute dating can give you the exact age of the rock. This is accomplished using radioactive dating, aka radiometric dating, and this is based on the regular decay of certain elements. So if you're looking right here on our graph, if we were relatively dating, I could tell you that this layer right here is older than all the layers above it, or that this layer right here is younger than all the layers below it. That's relative. But our numerical dating, if I wanted to date these layers right here, and by the way, it works best and it's most successful with igneous rocks. So typically we will only absolute date igneous rocks. There we go. I can absolutely tell you exactly when these were formed using absolute dating. Like this was formed 494 million years ago. This one was dated 500 or created 510 million years ago, while this one was created 545 million years ago. We do that by calculating determining and then calculating the remaining concentration or the remaining amount of elements in a rock. Like I said, late 1800s is when this was discovered. It was discovered by Henry Becquerel, that's the best I got, and Marie and Pierre Curie. So pretty significant scientists, pretty awesome that they discovered this, and we've been absolutely dating elements ever since, or rocks ever since. Here's an example of what you might see on a radioactive rock. So the green part's the radioactive, I do believe, and then as it breaks down, it could become a different color, or it could just look the same and be a different element altogether. Phenomenons of radioactivity. So some elements such as uranium and thorium are unstable, meaning that they decay spontaneously. So this would be like just for no reason at all. Typically when things happen, like we have explosions, there's an igniting event. But if our elements are radioactive, they just decay without that pushing event, like to light a bomb, or not a bomb, to light TNT, like dynamite, you have to first light it on fire. This would be like if dynamite just exploded for no reason. That would be what an unstable atom is like. So spontaneously means that it happens without anything else influencing it. Nothing causes it. To estimate the age of the rock, we often look at the ratio between the parent amount, or the original atom, such as uranium, and the daughter product. In our uranium example, lead is our daughter product. So this is the parent is the unstable element, what is going to be reacted, and the daughter amount is the product, or what results after the parent has split apart. Again, uranium, lead is our daughter product of uranium. For a particular radioactive element in a rock, you want to determine the present ratio. So we want to know how much of the daughter over how much of the parent. And that's going to give us a general idea of how old the rock is based on the half-life. Half-life, a definition for you, is the number of years for half of the original number of atoms to decay. So we've got number of half-life 0, so we've got all of the parent element or isotope. And then after 1 half-life, we've got a 50-50 ratio. And then after 2 half-lives, we've got a 75 for the daughter product and a 25% ratio. After number 3, our ratio decreases even more. I can't do the mental math, but this is only 12.5% left. And then we break down further to 6.25% of our parent isotope left, until eventually all of that's left is trace amounts of the parent and none of the daughter product, or all of the daughter product, and trace amounts of the parent. So as you can see, the parent element is decreasing. Remember, we call this curved line to exponential. So this is a negative exponential. It's not a straight line, it's a curved line. Okay, that's half-life. And to finish up our lecture, with radiometric dating, we can assume that the rate of decay, the half-life of a long-lived element, has not varied since the Earth was formed, meaning that it takes 704 million years for uranium to have one half-life. We're assuming that throughout those years, the half-life of uranium has not changed, so it's the same. This is an example of what we call in science uniformitarianism, big word. But this is the principle that the physical, chemical, and biological laws that operate today have always operated in the geological past. So that's just an assumption we make as scientists and citizens in general. So we assume that. All right, again, to calculate, go back to this, the ratio of the half-life, you put the daughter product over the parent product. If the daughter product is larger than the parent product, then you can assume that more than one half-life has happened. If the parent product and the daughter product are 50-50, you can assume that only one half-life has happened. Okay? Awesome. I hope you have a great day. That's the end of this lecture. Please submit your notes via picture if you took them by hand or by submitting the document. Have a great day, and I look forward to seeing you tomorrow.